Hello once again, and in this video I'll be continuing the discussion about convection. Before we started this topic, I introduced two types of convection, namely the forced convection and the natural or free convection. Today we'll just be discussing forced convection. So before we begin, I wanted you to take this quiz. So there's a short quiz after this screen, and you just have to answer if the types of the setting or the problem is a forced or a free convection. I wanted you to understand the forced and free convection in a way that you understand how the concept goes well, so that you won't be confusing yourself when you're solving problems involving such kind of convection when we don't actually tell you what specific kind of convection happens on the problem. So let's get into it. So I hope it made some clarity in your mind about what particular type of convection that you have in such cases of problem. So just remember, when fluid is forced through the use of mechanical means, let's say pumps, fans, or even the problem doesn't tell you that there's this pump that is used to have this fluid conveyed, there are still cases that you would still consider this as a forced convection, well, because it doesn't naturally occur. Now, on the other hand, if this convection appears in a way that the fluid the material is just actually exposed to a certain environment, that's typically what we call the free convection. So now we move on to the discussion of forced convection, and I wanted you to take your Paris Handbook and some highlighter if you want. So of course, I'm not forcing you to highlight or mark your Paris Handbook, but this will be very efficient when you're solving this kind of problem, since there's a lot of equations that are inside your Paris Handbook, and you might get confused when you're trying to solve this. So I will still be using the 8th edition in this discussion, since that version is actually the 9th edition version of the PDF file is not yet the official version. But of course, I will be adding the specific tables here, just some kind of subtitles. Okay, so we start by defining the boundary layer first. Before we start solving, let us just understand how it goes for such kind of boundary layers. So we have two boundary layers. We have the velocity or the hydrodynamic, and then the thermal boundary layer. So to understand, to explain that well, I have a flat plate here, and this flat plate is on its side view. So imagine this is like a plate where you're just looking at the very side of this flat plate. The leading edge is what you can see something like at the front of that plate, and then by the end of that plate you'll be having that trailing edge. So in cases like an airplane, the leading edge would be those that are exposed mainly to the air, and then the trailing edge would be those that you can see by the window. Basically, when we talk about this velocity or hydrodynamic boundary layer, we're basically referring to the fluid that goes past through this plate. So there are ways that we can describe this layer. Okay, I mean, this boundary layer can be bounded boundary layer or unbounded. So let me just some kind of, let's say this can be bounded or unbounded. When we say this, the one I'll be showing is something like an unbounded boundary layer. So what we mean by unbounded is that I just have one boundary here, and then the fluid will just pass through this boundary without any boundary at the upper part. So when we say bounded, I can actually add some layer here at the top. So I can add some layer around here, and then it becomes bounded boundary layer. Since if the fluid will flow right through this inside this hydrodynamic boundary layer, I mean this pipe. So in this case, it has a boundary at the lower and the upper part. So we call this the bounded boundary layer. So those layers that will be forming near the boundary would be called bounded. And we call this flow internal, simply because it's inside the pipe, and those that flow on the external of a certain, let's say, a material, for example this plate, will be called an external flow. Well, simply because it is logical to say that it's external because it flows outside of that flat plate. So let's try imagining these fluids that enter here with layers. Now when we talk about layer, let me just use some different color. Now when we talk about layers, you could imagine this fluid entering as if they are very small layers of water. When we talk about these kind of layers, you would understand that if you have an oil and then water, there will be a layer that is formed. But in this case, we're not considering two liquids, we're just considering one. And for example, this is water. That water goes past through this flat plate. And imagine this happens when, for example, we have some flood, and then there's just this road. That's just actually an example of what's happening here. Imagine the flat plate would be the road, and then the flood will be the fluid. And assuming that the flood would just have this water, and disregarding all the constituents that are inside this flood. So anyway, so in this case, we do have some kind of very thin layers, infinitely thin layers of, let's say we call this the streamlines. Now, you might be thinking, what happens when this fluid enters, it starts flowing past through this flat plate? Now, I want you to understand that fluids work in a way that we're considering some streamlines here, and these are the infinitely many streamlines. Now, at the start of the fluid entering this flat plate, you could see that the fluid will just go right through it. But you have to understand that in cases where we're going through this leading edge and then trailing edge, you should understand that there's some kind of resistance that is offered by this flat plate. Well, that's simply because of physics. So you should have a resistance to any kind of material. And this resistance, so you might be thinking, how is that resistance possible? You can't actually see that, and if you're just conveying some fluid, you will see that the fluid flows like freely. Well, yes, that's true, but in essence, the truth is the flat plate actually exerts this resistance and somewhat retards this fluid layer near the flat plate or the boundary of this flat plate, and then the velocity of this streamline becomes 0. So it's like saying that the velocity of the fluid near the boundary, this is the boundary that we have, the flat plate, becomes zero when it comes, it comes closer to this boundary. So in this case, if we would represent this as vector arrows, we mean something like the longer the arrow would be, that the velocity would just be greater. So if we would be representing that, we could say that this would be extending further. So imagine these fluid layers. The higher you move away from the boundary, the more you are not able to resist, because the boundary or the flat plate would be resisting those that are very near its boundary. So as we move further away from this, as you can see, this flat plate, we could see that we're having this, the fluid becomes more freely flowing, or the streamlines are more capable of going to a straight direction. So this is how it goes for our fluid. So imagine the resistance that is offered by this flat plate, and this resistance would be able to like retard this streamline that is near the edge. So we call this condition the no slip condition. Let me just like right here. So this condition, the no slip condition, means that the velocity of the streamline near the boundary would be equal to 0. So in this case, then that's how it goes for the flat plate. And remember, we're considering the unbounded boundary layer. And when we talk about the velocity or hydrodynamic boundary layer thickness, we're actually measuring the region wherein the velocity of the free streamline would be around almost equal to the velocity at this portion, which is just the end of the thickness. So to give you some idea, let's say we call this the boundary layer thickness. So this boundary layer thickness, as you can see here, the velocity here is just less than the velocity on the upper portion of this layer. So in this case, at this moment or at this region, the velocity of our streamline starts to somehow equal to the velocity at the upper region. So in this case, the hydrodynamic boundary layer thickness or the velocity boundary layer thickness would be equal to that distance. So that's the distance away from the boundary of our fluid conducting medium. So in this case, let's say we have we regard the velocity of any fluid as u, and then u infinity. We call this the free stream velocity. So the free stream velocity is, usually you're encountering this, but you don't actually know that it happens when you're solving problems and there's something like this. Water flows at 4 meters per second. That's the free stream velocity, simply because it's the average velocity. The problem is considering the velocity that's uniform along, let's say, along any kind of material that is conducting fluid. So in this case, you call that the free stream velocity. But if I would ask you, or the problem would say, the velocity near that certain boundary, I would say that that would be less than the free stream. So this velocity here, and any velocity that is inside this boundary layer region, which is the thickness, would be less than the free stream velocity. So in that case, if you wanted to like plot it using some, let's say, some x and y axis here. So if we take the ratio of our u, let's choose another color. So if we take the ratio of our velocity to the uniform velocity that is at the layer at the top, we would see that as we move on with the thickness that is moving further away from the flat plate, we could see there that it starts with as if, of course, it will not be 0, since we're just considering this no slip condition being 0, but it's not actually 0. It still has some kind of velocity, but a very, very small. So 0 will just be an open hole, so it's not considered a solution. But as we move further away from this thickness, we can see that the velocity, the ratio of this one would be uniform. Okay, and in this region, we can see that this is almost as if this is 1, where our velocity is equal to the free stream velocity. And when we say that we have u is equal to around 0.99 of the our free stream velocity, we can say that this is where the boundary layer thickness ends. And of course, passed through that layer thickness would be the free stream velocity. So this is like the free stream velocity. So this is how it goes when you graph this velocity or boundary layer. I hope you have understood what I'm saying. It's like this boundary layer gives a resistance to the fluid velocity. And while you're thinking about fluid, you should imagine that fluid actually has some kind of layers, and then these layers would be it's like they're streamlines, and when these streamlines are near that boundary, it will be retarded by the resistance that is offered by the plate. So whatever the condition that. And then you might be wondering why this is we're actually having some kind of more velocity here. The velocity is able to overcome this because the resistance that is offered by layers that are here will be much lesser, since the resistance would be coming from the fluid itself here. So it's like it's getting diminished as it goes farther away from the flat plate. So that's it for our velocity hydrodynamic boundary layer. So what if we try to add some another layer here? So for example, I will be doing some bounded boundary layer. So in this case, I'll be adding some kind of layer here. So in this case, we call this the bounded boundary layer. So that's just also simple. What we have here is that this layer would also offer some resistance. So it's basically something like this. So it's basically something like this one. Just like we're just mirroring what happens on the lower region of this boundary. So it will offer some resistance, and then this velocity would be also lower, but it goes higher and higher as we move towards the center. Okay, so this is how it goes for this when we have some kind of hydrodynamic boundary layer, bounded boundary layer. So can you see it clearly that this looks some kind of parabolic? And that's how it goes for fluid pipes. The velocity profile for our pipes, the fluid that flows inside the pipe, is actually parabolic. But if it is unbounded, so imagine we take this boundary out, so it will be something like the one you saw earlier. It goes something like that, and not parabolic, but something like exponential. No, not exponential, but increasing. So if we add something like another boundary here, so it will not look like this, but this one looks like parabolic. Okay, so that is very important, because if you're asked to, what is the velocity profile of a fluid that enters a pipe, you would say it's parabolic in nature. And then the maximum velocity, where do you think you'll be finding the maximum velocity? So the maximum velocity of that fluid will always be at the center line region of the pipe. So at the very center of that pipe, you would see that the velocity is at its highest. Okay, and there are ways to compute for the velocity at the region of this boundary layer thickness. And by the way, there is also a boundary layer thickness here. So let's just add some boundary layer thickness again here. So yeah, that's how it goes for the unbounded boundary layer. And the thing is, it's just the same for what happens if you're just considering this u over u infinity, or the free stream, if you're comparing it. As we move towards this trailing edge, the fluid starts to overcome most of the stress, and then the profile would just be around. I mean, as we move towards this trailing edge, the velocity profile would be more evident. So we call that the fully developed flow. So in this case, it doesn't look more like parabolic. It looks like more, flat for parabolic. But after some time, if it goes near the trailing edge, so that's almost at the end of our pipeline, the streamline would just look like this. Imagine the arrows like this. So we call this the fully developed flow. So that's how it goes for our the momentum of our fluid. So I think you have heard already this some kind of laminar, turbulent, and transition region, and there's this something like laminar but not fully developed laminar flow. So that's how it goes. When we talk about fully developed flow, we're considering the velocity profile of that fluid at the very end of this near the trailing edge of our pipes. And of course, if you don't have this some kind of boundary layer, the flow will still be developed, but it is more evident in bounded regions, since that's the nature of fluids anyway. So I would also like to discuss or review some of your concepts in momentum transfer unit operations 1. So remember this layer. So this has some kind of velocity. We call that the velocity of the fluid. That's why this is called the velocity boundary layer. But what if this, along the way, these streamlines or this region suddenly becomes, let's try to remove some of this so that we have some kind of space. I hope you've understood this U infinity being the free stream or the speed of the fluid at the middle section, and then the no slip condition where the velocity of the fluid becomes 0 near the boundary. So anyway, so let's try to have some kind of analysis on these layers of fluid. So if this layer of fluids becomes something like this, so as we move forward on this flat plate, let me just try using this kind of one. So if these fluid layers, for example, as we move further away from the boundary layer thickness, so let's just have some kind of parabolic instance here, and then something like this. I think it should be better if I use pencil. So it goes something like this. The second layer would be something like that. It curved a little, and then this one also curved a little, and then this one did something like this. The free stream goes like this, and then so as we move towards this trailing edge, you can see there that the layers of this fluid started to like mix up. So in this case, when the layers of this fluid start to mix up, we call this the turbulent region. And when we just have some kind of free stream here wherein the layers are not actually mixing, now I want you to think that these layers are they're just the same fluid, but imagine that these are dissected into like of infinitely many layers. So if these layers are not mixing, we call this the laminar flow, and then the Reynolds number for that is 2100 less. Now if we have some kind of transition region, the fluid layer starts to like mix up, and then when we have something that we call turbulent flow, the layers of these streamlines will just be like messed up and disturbed. We call this the wakes or the vortices that are formed during this water transport, and it happens when the fluid has a very large velocity. So the inertial forces of this fluid overcomes the viscous forces that are inherent in this particular fluid. So in this case, we develop the turbulent flow. So again, when we talk about the Reynolds number, this is the ratio of the inertial force over the viscous forces. So each fluid contains some kind of viscous force. That's what we call the viscosity. And if the fluid has a very fast speed, or the fluid has a very strong inertial force, somehow it overcomes this viscosity, and then the Reynolds number becomes higher. And that's why it is logical to say that if the fluid is viscous, most of the time it will be laminar, since the inertial forces are a lot greater than the viscous force will be a lot larger than the inertial forces. So this is how it goes for, just a short review of your Reynolds number. This is the laminar wherein the layers of the fluid do not actually mix. And then there's this transition where it starts to mix, and then there's this, the final or the turbulent, in which it is disturbed, or the layers are just disturbed. So, in the boundary layer, you can see there that, actually this disturbance actually starts, right after the, boundary layer thickness. So, and near this trailing edge. So when we start to have something like, the fluid is starting to just conduct inside or above above the plate, the fluid would be much more stable than, this at the trailing edge. But remember that the velocity profile, the one I drawn something like a parabolic, it will also be evident at the trailing edge. Okay, so that's it for our velocity or hydrodynamic boundary layer. So there exists a velocity or boundary layer whenever there's a boundary. So that's a fact. So whenever a fluid pass through, any fluids that pass through any kind of surface, or inside, or even if it's external or internal, it will always have this boundary layer or hydrodynamic boundary layer. But there's a difference in that when we talk about a thermal boundary layer. It only exists when there is a temperature gradient. So remember that if there is no temperature gradient, this thermal boundary layer will not exist. It will never exist. So even if you have this flat plate and then it has just the same temperature, the thermal boundary layer will not exist. So how does it work? So if we set, for example, Ts being the temperature of this flat plate, and of course Ts is not equal to the free stream temperature. We call this the free stream temperature. That is the temperature of the fluid, just like the average temperature. So what happens that, of course, the fluid will enter, again, just like this kind of drawing. So we'll also be doing something like this, the streamlines. I would like to have some more accurate drawing here. So the streamlines are like that, and then this boundary layer will only exist. Of course, the velocity boundary layer is already there since we have this kind of boundary. But if we have here the Ts not equal to Te, so the temperature of the plate is not equal to the temperature of the fluid, we will have something like a thermal boundary layer. And then the thermal boundary layer, as you can see here, as the fluid temperature comes in contact with this boundary layer, the temperature also comes closer to our Ts. So for example, I have here T. Just an assumption of, let's just talk about this like streamline, and then it has a T. This T would be greater than Te, since, for example, Ts is greater than Te. As this as this velocity streamline comes closer to the surface of this flat plate, which is higher, it is logical to say that the temperature would also be greater than the temperature of the free stream, which is the temperature at the top layer of this fluid. So if it is bounded boundary layer, then that's at the center line. So the Te would be at the center line, and T would be greater than Te. So that's just how it goes for our thermal boundary layer. What we have here, of course, is also the let's call this the Ts, the thickness of our boundary layer. The thermal boundary layer. So I would like to add some X here so that it represented as velocity boundary layer. And then this one is our thermal boundary layer. So in this case, it behaves something like this. So it will have some kind of thickness from the plate, but we're not considering here the velocity, but we're considering the temperature gradient. So at this point where we already have some kind of free stream velocity, we have here TE, but any portion here that is at the region of our thermal boundary layer would be something like T is greater than TE. So in short, if we wanted to like graph this, we could see that as we move towards, so we call this the distance from our boundary. So as we move towards this, further away from this TS, we will be reaching a point wherein this is equal to TE. And if you wanted to like take the ratio of our temperatures, what we get here is TS minus T, and then we have TS minus T infinity. So this Ts minus T over Ts minus T infinity, so remember this Ts is the surface temperature of our material, and then our T here is any temperature that is of experiment, and then this T infinity is actually the TE. So I'm used to like using TE since we'll be using a lot of TE. That's the free stream velocity, or the uniform velocity, as you may say. So as we move towards the center, the edge of this flat plate, we could see there that we come closer to the value of T. And in this case, if T becomes very close to the value of Ts, and that happens when the delta Ts is almost 0. So in this case, this becomes 0. So like the velocity profile, we could see that there's just this kind of graph, and there's just this 1. And in this case, will be, if this is equal to 1, we could say that this T is actually equal to T infinity, or TE, and that happens when we're past this thermal boundary layer thickness. So that's it for our thermal boundary layer. I hope you've understood how it works. In velocity or boundary layer, it's just, this is just a concept of, introduction to force convection. That's why I wanted you to understand this. And this is very essential when we talk about this force convection, by the way. So when we talk about velocity or hydrodynamic boundary layer, we're referring to this some kind of velocity gradient that happens when there is a boundary, or the fluid passes through any kind of material that has this solid boundary. And at that boundary, that region where it is closest to this solid boundary, the velocity would attain this no-slip condition, meaning the velocity is equal to 0. And then at the very center, if it's bounded, would be that the center line would be the free stream velocity, but if it's unbounded, then the upper portion of that fluid will be the free stream. Now, the thermal boundary layer will only exist when there is a temperature gradient, and then this temperature gradient will also have some thickness, and we call that the thermal boundary layer thickness. So as the fluid comes closer with that temperature of the, as it comes closer to the boundary, it will have a temperature that is a lot closer than the temperature of this boundary itself. So if, for example, the temperature of the surface is greater than the temperature at the free stream, the temperature at any point that is at the region of our thermal boundary layer thickness would be much less than the uniform velocity of our, uniform temperature of our fluid. So that's a different story when the temperature of the surface is lower than the temperature of the fluid inside. So that would be that the temperature at the thermal boundary layer would be less than the temperature on the uniform or the free stream, since the temperature here is a lot lesser. But anyway, in cases where we have fluid and we have a temperature gradient, we should know that convection will happen. And if we want to take the ratio of this, we have this velocity or hydrodynamic boundary layer thickness. If we take that ratio, so we take the ratio of our thickness, both the two thicknesses here, So we have the velocity, and then the thermal boundary layer, we used to name this the Ts and then Ts. So we call this another dimensionless group, which we call the Prandtl number. So of course from the scientist Prandtl. So sometimes we refer to this as NPR, sometimes it's just PR. So you are free to choose whatever you want. If you want to like save some space, then use this PR. I'll be using any of these from time to time, so get used to it, okay? So this is what we call the Prandtl number. So basically, if we would give a definition for this Prandtl number, that is the diffusivity momentum ratio with respect to the thermal diffusivity. So Prandtl number is very important in convection, since convection, remember, we're considering the the heat here and the fluid. So this is Prandtl number is very efficient to giving you the ratio of this momentum. This is the momentum because this is generally influenced by the velocity, and this is of course the the heat, since it has a thermal boundary layer. So that's how it goes for if you wanted to like take the ratio, you will get the Prandtl number, but we do have some kind of formula there. And as what I've mentioned before, since I've already discussed some kind of dimensionless number, which is this Prandtl number, let's have some review of your dimensionless numbers that you'll be using in this discussion. So these are the three most important dimensionless numbers, and this is also an optional dimensionless number if you wanted to like memorize it. But for now, for force convection, we only have 4. So this Reynolds number, I know you're quite familiar with this. This is again the ratio of the inertial force. So we have the inertial force over the this viscous force. So this inertial over viscous forces can be represented by an equation for the Reynolds number, and that is equal to the inertial forces, that is the density times the velocity of the fluid times the hydraulic diameter. So divide this by the absolute viscosity or the dynamic viscosity. So that is how we solve for the Reynolds number. Sometimes they joke about this, like the bahay kugo, magtanim ay d0. So that's how it works for Reynolds number, the d0 over mu. So the numerator would give us the inertial forces, and then the viscous forces is of course the viscosity. Now there are ways we can also represent this as something like a kinematic viscosity, wherein we would be dividing the numerator and denominator by the density. So what we get here is simply the velocity times the hydraulic diameter over the kinematic viscosity. So what's difficult about these unit operations, that the representation of the letters are very familiar. They're very close with each other. This is something like I think it's nu from Greek alphabet, and this one is V, so don't get confused with it. That's why people would always be using this, as this is the more it is easily understood and easily remembered formula than this one, since we usually give the viscosity as dynamic viscosity rather than kinematic viscosity. And the difference between those two is just if you have some kind of absolute viscosity here or dynamic, that's the same. You divide this by the density and you will be getting the kinematic viscosity. And by the way, dynamic viscosity is the viscosity wherein the fluid is at rest, and it is it refers to this some kind of force that is required to move that fluid. So that's how it goes for this dynamic viscosity. And since we can solve for the Reynolds number, and then we'll be having some kind of values, and since these are all dimensionless numbers, they don't have any unit, but they relate properties of fluids. So anyway, if we have some kind of laminar flow, so you're very familiar with this laminar flow, so the Reynolds number should be around greater than less than or equal to 2100. So some books would give you something like 2200 or 2300. So some books would do that, but can use any of these. We're just considering at up to 2300 being a laminar, and then for the turbulent, so we usually have some Reynolds number greater than around 1900. So in this case, any value that is in between these two, so we will be having some transition state. So any value in between these. Okay, so usually the values of our transition is much more, much more less common than existing the laminar and turbulent flow. Now, some books like the Gene Copley's and the Paris Handbook, it will give you that the turbulent region would be around Reynolds number of greater than or equal to 4000. So there are a lot of experiments that were conducted that they arrive in different values here. But in this case, since of course we have to be like consistent with everyone, so let's use just this laminar being at the Reynolds number that is at 2100 less than or equal to 2100, and then for the turbulent region we have this 4000, since the Gene Copley's and the Paris Handbook are using that. Actually, Reynolds number for Paris Handbook will be around 5000, but some correlation for Darcy's equation and other familiar equations give us the 4000 being the turbulence, so let's just use it. And then the transition would be in between them, so we could say that the transition region would be from 2100, greater than 2100 but less than 4000. So in that case, will be fixed with how we use or how we define these regions. But the good thing about it is that when we solve something like fluid mechanics, when it is laminar, it's like very laminar, since the Reynolds number would be around just less than 1000 or just 1000 something. And when it's turbulent, it's like it's highly turbulent. The values would be like 10 to the 4th or to the 5th. So it makes us easier for us to classify the fluid, the region of fluid. By the way, I'm discussing this Reynolds number because when we solve forced convection, it is very essential that we identify the conditions first. And one condition that we need to identify is the regime of flow for our problem. So the next one will be the Reynolds number, and I've already discussed this. This is the the hydrodynamic boundary layer thickness divided by the the thermal boundary layer thickness. And in this case, if we wanted to give some kind of formula for our Reynolds number, then the Reynolds number is simply, since we're considering this velocity boundary layer being the ratio, so we could say that this is the viscosity or the dynamic viscosity divided by the density, and then we take the ratio of our thermal boundary layer, that is the thermal conductivity, over the density and then the specific heat capacity. So this is also what we call the thermal diffusivity, and this one is the diffusivity of momentum. So if we would be canceling out the densities here, we will be left out with Cp, which is the specific heat capacity, times the absolute viscosity or the dynamic viscosity divided by the thermal conductivity. So if you have something like thermal diffusivity, which is we call this the alpha, that is equal to K, thermal conductivity, divided by density times the specific heat capacity. So if you have this, you can substitute that with our equation, and then you'll be arriving at this some kind of so we can also do this, I think. Okay, or also it could be that since this is absolute viscosity divided by density, that should also be equal to our kinematic viscosity. So in this case, we'll be having something like V over, that is how we define this, the kinematic viscosity over our thermal diffusivity. But it is better to use this, since this is a lot easier to remember. And of course, the thermal diffusivities are actually not given in your Paris Handbook. I mean, the table of thermodynamic properties. So, it is better to use this one. let me just box the equations that we will be using more often. Now, Nusselt number is also a very important dimensionless number, since it gives us the relationship of these Reynolds and Prandtl number. Usually, when we talk about the Nusselt number, it gives us a function of the Reynolds and Prandtl number. So this is usually how it goes. So there's a lot of correlation that gives us the Nusselt number, and this one would simply give us the relationship or the ratio of the resistance to heat flow and convection resistance to heat flow. So if we're considering a diameter, so if we're having this kind of conduction over convection, so this one is conduction and this one is convection, and we're considering the resistance, remember, so before we used to solve some kind of the resistance of conduction, that is over K, since we call this the resistance, and if this is the thermal conductivity, then the reciprocal would be the resistance. And then we divide that with, of course, the convective heat transfer, which is the resistance to convective heat transfer, so that is, of course, the reciprocal. So we used to like add this as our resistance when we have some kind of combined convection and conduction. And in this case, if we would be rewriting this, we'll be having something like HD over K, and H is the heat transfer coefficient for convection, and then K is the thermal conductivity, and D is, of course, the diameter. But if it is the element that is in contact with the fluid, then that is the value of that element that we're thinking of. This can be also X, L, or whatever the value, depends on the problem. And now, finally, we have the Peclet number. So, Peclet number is simply the product of the Reynolds number and then the Prandtl number. So, if you just be having some kind of values for this, then you just multiply them, and there's just this Peclet number. Now, some equations will be having some kind of Peclet number on the equation, so you can just multiply the Reynolds and Prandtl number. Sometimes they use it to simplify the equations. But these three are the main important dimensionless numbers that we need to remember. Peclet is the product of Reynolds and Prandtl, but Nusselt is a function of the Reynolds and Prandtl number. So instead of just multiplying, this Nusselt number would have a lot of additional components on the function, since it's just a representation of this function. And Nusselt number will be equal to very specific types of, it will give you equations that vary depending on the condition. That's why I presented different kinds of free convection and natural convections before, since we'll be using a lot of Nusselt number here. In today's video, you will learn how to review the Reynolds number and then the Prandtl number, how to solve for it, and then the Nusselt number, and how to use this Nusselt number in computing for H. Since, as you can see here, we have H. Remember, I used to say that in any kind of convection, there's only one formula for Q, that is A, H, and then Ts minus Te. And since this is just the area and then this is just the temperatures, this one H here is the one that you need to find. And H will be coming from the Nusselt number. This one is HD over K. But to do that, to be able to find H, you should have solved for this Prandtl number, which is Cp mu over K, and then this Reynolds number. So I don't think you will be having some kind of problem in Reynolds number, since you've already known this. But for Prandtl, you should be practicing for this, and of course the Nusselt number. And I would like to inform you that the computations here would be a little tedious, and I'll be doing some pre-solved values here, so I will not be like computing along with you, just to minimize the time. So probably the one that I have computed would something like, I don't know, if I have mistyped something, then that would be different from your answer, but I've already rechecked these values. So if you have questions, just let me know. So let's start by solving some problems in your module So I have here your module, and by the way, I would like this is the boundary layer I was talking about, and I would also like to emphasize this. Let's just have some overview of the equations. The one in the red here is what appears in your um, Paris handbook, and the red means that you don't have to like memorize this since it's already in your Paris handbook. So you just have to remember where it is written. I have already included it in the 8th edition, but I mean, you have the 9th, so I'll be writing it somewhere here. So if you have your Paris handbook now, you can check on the chapter 5 since this one is chapter 5. So this chapter would give you, sorry, this chapter 5 would give you a lot of equations. So I think yours is also written in here around this forced. Let's check for forced convection. So here there are a lot of equations here, and we'll be using that. So for your module, we have here as what I've mentioned before, this is a case-to-case basis where you will be using different kind of equations. So for this one, we have the fully developed laminar velocity profile and then constant wall temperature. So for any case where we have a fully developed laminar flow, that's the case when, as what I've mentioned before, the velocity of the velocity profile is nearing the trailing edge, and the fluid has already formed this parabolic velocity profile. So in cases like that, and we will be assuming that whenever the problem doesn't tell you that it is a fully developed flow, we'll be using that kind of condition. So we'll be using this for the velocity for the fully developed flow. And if and this one is I think this one's the easiest. So this is an approximate of Cedar and Tate, and this one is, I think, the one used for McCabe. And when we had this board exam, this one is the one that they use. So I want you to use this since this is the Paris Handbook edition. But I want you to check your answers using this one. But this should be just used for developing laminar velocity. So the thing about this problem is that we can't know for sure what kind of velocity profile that they exhibit. So it's better to use the most accurate one. But this one is an approximate, so you can check your answer with this, and your answer should be like close to each other. Now there's one, and remember there's just some exception for this, so remember to use this. And the fully developed flow for the transition region and turbulent flow, so we'll be using this for the transition and the turbulent flow. And lastly, we have this simpler equation for Cedar and Tate. Again, he also had some kind of simplified equation, and we'll be using that to check the answers. So we have here D, and there's a lot here. You can just browse over here, and I will not be like discussing all of it. Let's just use the one that we'll be having depending on our problem. By the way, I actually forgot to write one equation here that should be after this. I think after this one. Yeah, after this, the last one here. Since this is just for the laminar flow of isothermal flat plate, I think I forgot to write the isothermal flat plate and then the turbulent flow. So that's just after that equation here. So the forced convection, the one that I copied here is this one, and then this one would be the one I'm talking about, this particular equation. So this one, since this is for turbulent, and that's actually a very important equation since most of the fluids that are in gaseous phase would be like turbulent. So yeah. So let's start by solving one of the problems in your module. I mean 1 or 2 or 3, so whichever we can. Okay, and by the way, I wanted to emphasize this 2 here, since I wasn't able to solve this, and will not be solving this since this is actually a fin, and I wasn't able to give you the formulas for fins, so let's just leave it there, okay? And I will not be including something like that in the exams. So, by the way, let's move on with this convective heat transfer. I think I have already solved for this 3. So, let's move on with this convective heat transfer. Let me do the first 3 problems for now, since I think this will be very time consuming if I try to solve all of them. So for our first problem, I wanted to read it and understand it, and I will be giving you something like 3 major steps that we need to understand to solve for any kind of convection. So yeah, I hope you've read the problem and understood it. So I'll be giving you some tips to solve any problem in convection. So the first one is that we need to determine the conditions. So when we talk about determining the conditions, we're actually we need to find the geometry, that is where does this fluid flow, or if it's external or internal, and then of course the region of flow. So that's the condition that we need to understand first, and then after determining those 2 points, then we select the equation or the appropriate equation. And this is very important, since when we selected the wrong equation, then of course we won't get the correct answer. And the number 3, last one, of course, would be like we evaluate to find what is asked. So that's just how it goes for any problem solving, I guess. We evaluate at the end. But the very important one here is the first 2. We need to determine the conditions and then select the appropriate equation. So that's just how it goes for any kind of forced convection and natural convection. By the way, okay, so never mind. Let's just start. So the first one is we determine the conditions, the geometry, and the region of flow. So the first one is the condition here is that, the geometry here, we have a 50 cm square plate. So if we have something like a square plate, this is something like a square plate. And it says here that it's like this, determine the conditions like finding the given. So we're finding the geometry here. We have 50 centimeter on each side, so this is a square. And then the velocity is 30, so let's just have some dimension here. Let's say x, this is equal to 50 cm, and then it blows across the 50 cm. So imagine this is our oxygen blowing through this. Okay, so the velocity of our fluid is 30 meters per second, and then the plate temperature, so that is T sub S, since that is the material, that is 127 degrees Celsius. And then for our fluid, we have the pressure that is at 2 atmospheres, and then the temperature of our free stream would be TE, that is equal to 27 degrees Celsius. So that's particular all our given. And the next thing that we need to do is to find the region of flow. And by the way, if we would be adding some geometry here, we would be having something like a plate or a flat plate that is also isothermal, since it is maintained at a constant temperature. So we have an isothermal flat plate, and then we need to find the region of flow. So we need to calculate the Reynolds number for that. And this is also some kind of forced convection. So this one is a forced convection simply because you don't actually blow oxygen. You don't naturally blow oxygen. It's oxygen only. So the thing is, natural convection mostly occurs in which the object is just exposed to the air, and that's air. So if you're having this oxygen that is blown So you should have something like a pump there or a fan or whatever is that you'll be using to blow some kind of oxygen. So even though this problem didn't mention any kind of mechanical mean, is that it actually gives you an idea that that's still a forced convection, and this is something like an unbounded boundary layer where because we're just having some kind of one plate here. And there's this is actually at the top view of that, but if you wanted to like give you the better view, this is the 50 cm, and then this is a square plate. So I don't know about the thickness, but this is how it goes for that. So that's the oxygen, and then we need to find the region of flow. So with that, we need to find the Reynolds number. And since that's a plate, I'll be writing some X here. That means that I'll be evaluating the Reynolds number not in the diameter, but the measurement of a side of our plate. So we get, remember that is the diameter, but since we don't have any cylinder here, I'll be using X, since that's the length that is considered in our problem. So that is X, and then we still have the density, but the density will be evaluated at the film temperature, and then we have the velocity of the fluid divided by the specific the viscosity at the film temperature. So I'm adding some sub F there to specify that I'm evaluating them, all of them, in terms of the film temperature. So when we talk about the film temperature, that is simply equal to the average temperature of the free stream and then the material temperature. So that is because we need to evaluate all of our physical properties at this film temperature. So that is 127 plus 27 over 2, and then what we get there is simply the average of the two would be 77 degrees Celsius, and that is equal to 350.15 Kelvin. This is the temperature we'll be evaluating all of our physical properties for our fluid. So with that, let's have some look at our oxygen at the Paris Handbook. Because at first we need to find the region of flow, since we're just doing number 1 or determining the conditions. And by the way, what I did here is actually also written in your Paris Handbook. If you'll be using some kind of equation, you also have to use the film temperature or the bulk temperature if you have some fluids with in and out, since you should always be taking the average of the temperatures. Well, in some cases you don't, but the problem should be specifying that you don't have to do it. So in this case, I'll have 350.15 Kelvin for the oxygen. So let's head on to our Paris Handbook, and this is your 8th edition. I'll be using this, and if you would be looking at the thermodynamic properties, you would see here that there's this thermodynamic properties of oxygen.